So we've got a number of different types of units in this neural network that we're going to be talking about. So we're going to be talking about hidden layers, which are often at least originally described as neurons, even though they're not really similar to neurons at all. Just kind of a reminiscent kind of metaphor that they have inputs and outputs. So if I have a drawing, for some reason my drawing from previous years is gone, the fundamental structure that will get us through kind of stuff today is this idea of a bunch of units and a bunch of inputs. And so every one of these is, well, the connectivity can be done in any way. So what I'm drawing here is that they're fully connected. So I'll talk about them being fully connected, and this is what we mean, that basically every node in a particular layer connects to every node in the next layer, right? So it gets very messy. And we'll talk about there being the input layer, some number of hidden layers, and an output layer, right? That's just a very simple design, and it kind of expands from there. But each one of these nodes is one of these units or a neuron, and these links that we're talking about between them, mostly these days we're going to talk about forward links, where we go from the input, and I mean the main idea is that out here is data, and out here is your it could be your prediction or your classification, your regression answer. It could be your anomaly detector solution. It could be anything, right? But theoretically, for neural networks and over the history of them, there's been models that do things in lots of different ways. You can have links that go forward and backward. You can feed information kind of in loops. You can have the links between kind of these layers of nodes be fully connected or partially connected, and we will see some examples of that. Those are the main parts. Another main part we'll talk about is this activation function, which adds nonlinearity to the model. So that's kind of a very high level. For that first unit, we did talk about this last time, I think. Each one of these units that we're talking about here basically has a bunch of input signals, which are the individual features in your data set. Something of our COVID data set, they're going to be age and latitude and longitude, and diagnosis properties. In an image, they would be individual pixels, right? And we're combining them together in this function. And it seems so long ago now, I'm forgetting that the previous lecture ended. I know these are the next slides, but I don't know. Yeah, so we can get to that. Oh, okay, that's what I figured. Sorry. Okay, but we showed that sigmoid unit, so that should make sense to people, hopefully, right? That this is the main neuron, right? Which is not really a neuron, so I don't want to write it on the slide properly, but that's the idea of that main neuron. And the weights that we're learning, the parameters of this function that we're trying to fit, are the things that basically weight the inputs on these, every one of these features coming in on the function that combines them, right? So you're literally learning these weights and adjusting them, and then it gets passed through a nonlinear function. So we've talked about sigmoid before, right? The logistic function, because it turns some arbitrary number, right? It can be anything from like minus infinity to infinity, and gives you something between 0 and 1, right? So it gives you a probability essentially. So that's the base one that people use, but we're going to talk about other ones that people use now that are probably more effective. But it seems similar to the idea of a neuron, because in a neuron in the brain, there's these inputs coming in. Your neurons in your brain each have thousands or hundreds of thousands of inputs. And at some point, enough electrical charge built up here or some chemical balance changes, and it sends off a pulse outwards. And it's kind of this spike, right? And they've noted that there's these spiking kind of patterns. Once it hits a certain threshold, it sends out a signal and then it stops, right? So you don't remember something until enough things have triggered it, and then you remember it. Or once you smell enough of a bad odor, it sparks, and then you get this disgust feeling, right? That's how our brain works. So the idea of this threshold as nonlinear came from this neuron idea, and it is useful mathematically because it helps the function be, I guess, more decisive and more general. So we'll try to talk about that as we talk about what a different function might be. Right, so somebody's asking about backward connections. Yeah, and so it's different than backpropagation, right? So today we're going to talk about this this structure that you go for, how you train a network. But so some older neural models, like Boltzmann machines and things like, so before 2010, there were people experimenting, and Jeff Hinton and even those people who kind of came up with a lot of stuff for deep learning, they were experimenting with networks that do have forward and backward connections, right? And so you train forward in one way, you get something, and then you learn backward, and you're still using backpropagation, but in the reverse direction to kind of update the model. The idea, sometimes they were trying to learn so that these nodes in the model, in the network, are not just weights in a function, but they actually somehow represented variables interrelated in some way. Yeah, there are other models that do that, but the standard stuff today, everything's forward. So it's important that whatever function we're using here and the entire representation of this neuron is differentiable, right? Because what we're going to need, so we're using sigma to represent this function, right? This whole thing here. And they were just combining things together as a weighted sum and then multiplying it by this function, and we know the derivative of this function. So all that's going to be important, because in order to update things, we're going to have to compute the derivative and kind of adjust weights by pushing it backwards, which is what this backpropagation algorithm is. So the kind of output for each different layer has its own formulation, right? So this net activation one is just the output that you get from after the first layer, right? Before we go through that sigmoid function, we've got, all the inputs and the weights, and this is just a simple kind of linear updating, right? Well, not updating, it's just the output, right? So the output of the nodes in the second layer just come from this function. But we can summarize that for every one of those hidden nodes now, we're going to have some output number that has been computed. Then in that hidden layer, we will do the same thing again. So we apply all the functions to, we're going to apply this activation function, right? So in our base model we're talking about there, it's the sigmoid, but it can be many different types of functions. So this is a really important part of neural networks, that there is a nonlinearity in there. You can imagine just having some deterministic function in here, a polynomial or a threshold or something, that kind of just turns the numbers into something else. But it's important that we say that it's a nonlinear activation function, right? Oops. And so what do we mean by that? We mean that there's going to be a strong threshold effect, that essentially some values are going to have just like that I talked about with the neuron spiking, right? At some point, once you smell enough of a bad thing, your brain goes like, oh, you get this sense of that smells bad. it doesn't happen until you get enough inputs to your olfactory centers, right? So if you had some kind of smooth linear function, things would just slowly build, and you get basically a linear mapping, and this whole thing would just become like linear regression or something. It'd be very boring. So what we really need is a non-linear effect, right? We need something where something changes abruptly. Like this one's still smooth, but it's quite abrupt, right? So people use this. Nobody uses this anymore, I think. I don't know if nobody, but I don't see it much. So this was the old one that was good. This kind of is just pure kind of simple idea. One problem with the sigmoid is that it kind of oversaturates. So there is a lot of space here, right? So if you basically get a whole bunch of inputs and the numbers are quite high, once you get up into this region, you can't really distinguish whether this neuron's on or off, right? And remember, we're trying to build a function that can represent anything. It needs to have the ability to turn a lot of its bits on and off really easily. So it works well, but it does have this tendency to kind of oversaturate. And so sometime in the last like 10, 12 years, people started using rectified linear units, which are actually simpler and yet improve things a fair bit. So it's still nonlinear, right? Because you can see that, in some part, my aim is really bad, of your model, you've got a low signal, and another part, suddenly you've got higher signals, right? But it also won't get oversaturated because you'll have this idea that they can keep getting stronger and stronger. So if you get more sensory inputs, it can still give you a difference between low and high. But if you think about this, it's weird, right? Because basically, this means that if you get any kind of low values up to some level, and remember, we're going to be adjusting the weights of this, right? So where this point is kind of moves as you're training based on data, but basically half of your data or a large portion of it, at some point, you're just going to zero it out and say, I don't want to even get that signal at all. So you're throwing away a lot of information. But also, I mean, the nice thing is that the derivative of this is simple, right? So it's 0 in these parts and just basically 1 in a part where it's increasing. But it still has problems sometimes in the sense that you're throwing away a lot of data on signals that are low. So they even have improvements on this that kind of try to get around some of that issue. And there's an entire kind of world of different activation functions that kind of get tried out and used, because one of the parameters essentially of a neural network now is, which activation function are you using to turn this like under constrained system, but adding a bit of nonlinearity to it in different ways. So if I go, because there was a page that had a nice this link here, some visuals of a bunch of these other ones that are more recent. Which one was I talking about? Yeah, so leaky ReLU gives a good example of helping to explain why sigmoid isn't good, ReLU is good, and even other things might be better. So what did we have here? Exponential. So they're all along that mode, right? So here's the original ReLU, right? Like I said, this gets you zeros and then some signal, right? So if you think about when we're doing gradient updating, so we talked about logistic regression, updating with gradients, neural network is going to be the same, although I have the slides a little later. For every one of those nodes, at some point, we're going to have the gradient of it, and we're going to have a signal on the output, which was like, did it get it right or wrong? And then we're going to basically weight that signal by the gradient we had, and we're going to use that to update the weights of it, right? And so if you talk about something like ReLU, you're essentially going to say that if you did well on it, the gradient for this is going to be positive, and you're going to basically learn from the things you did well, right? You'll have some number and you'll update the weights and it'll change. But if you did badly and you basically got the wrong answer, the ReLU gradient is going to be 0 and you'll just throw that away, right? So it speeds up learning because you're basically focusing on, for every node, you're focusing on the things that, on the right answers and trying to basically do more of what worked and do less of what didn't work in the weights on your network. And this kind of model essentially only looks at the positives, right? Which makes you learn very fast from the positives. If we go back to the original sigmoid, should be here. Sorry for the scrolling. Here we go. Oh, okay, we have them all here, right? The original sigmoid, you're learning from everything, and it's kind of this soft variation. So that was part of the reason why neural networks learned so slowly back in the old days. There's other reasons as well, and more data, different algorithms, but sigmoid's a bit not really aggressive enough, right? So ReLU is very aggressive. It focuses on positives, but it has this problem that you'd never learn from your mistakes. So what if your model gets a lot of stuff wrong, right?
I guess maybe we could have our own kind of discussion while this is down. I had a question about Mark's comment on how we only learn from positive examples. Maybe I'm not really sure what that means, but like all of the units that were non-zero, like all of the non-zero value units would still learn even if we got the example right or wrong, right? Oh, sorry.
No, it's great. Oh, I couldn't hear you either. Were you talking for a while?
No, I was just posing a question.
At the beginning, we did try to tell you, but I guess you couldn't. Like, there was we all tried to kind of, point out that no one could hear you, but I guess you couldn't hear us either.
Yeah, that's surprising. Yeah, and I saw it on the chat, so I've been trying to fix it. But it's only been 2 minutes. Yeah, I think I saw that soon. Oh, it's been 3 minutes. Where did I?
You kind of dropped off just as you were showing the big grid with like the 9x9 of all the different activation functions.
Oh, really? Okay.
You dropped out. Yeah, you had started talking about this for like 5 seconds, and then that's when it dropped out. So.
Oh yeah, no, I talked about it for a while. Yeah. That's weird. That's never happened before. It just, and there's no indication why it's dying. Sorry about that, everybody. I'm gonna have to do a lot of editing on this lecture. But sounds like people are having a useful discussion otherwise. So do we have any clarification or discussion? Somebody's asking about anomaly detection, basis functions.
Let's quickly follow up my question about the ReLU unit. You said that it would only train for examples that we got right, but wouldn't all of the units be like updated that were non-zero? Like, it doesn't matter if the example was correct or incorrect. All of the non-zero.
True. Yeah, I know. It's more that yeah,
learning is primarily done based on the the loss, right? So the higher the loss you have on the objective function, kind of dictates like how aggressive your learning is, right? Or that's how it should be, at least.
Yeah. So I mean, you're getting that signal from the loss function, and you're getting like the loss function takes into account, if you're doing supervised learning, how well it did on that particular output, right? And you're computing a gradient of all the weights, basically on, what was the impact of every weight of every node on producing that answer, right? And so then you get some output response, and you combine that into this loss function. But and part of the gradient is that at every level, when you're taking these output signals, the question is, what do you do with how do you add the nonlinearity, right? And so the way I think about it is that for values that are a lot more like for values that are stronger, where the gradient is high, and so there's a lot of impact of this weight on the output, you're going to get a strong response on these activation functions. And the ReLU is kind of effective because it's going to take all the high responses of that gradient, right? And use them to update the weights. But if you have a very low response or a negative response on your gradient for that weight, so it basically wasn't productive, right? So it's not necessarily whether the answer was right. I guess that's true, right? It's more about if you predicted, well, because I mean, it could be off, but if your model was getting classifying things in the right way or getting close to the answer, then the weights that were contributing to that, you want to basically bump up their value, and you want to either leave still or reduce the values of the weights that were contributing to, that were not helping to get that answer, right? And the way I see these values is basically focusing on the things where you see that the weights are contributing to getting the right answers, and then ignoring the ones where the gradient is negative, right? Because the gradient is negative, that means that weight was basically harming your answer or not being helpful.
Right, I see what you're saying.
Right.
Yeah.
But yeah, it may not be totally about whether it got the right answer on the label. I should try to be more specific. It's more about the gradients, right? But this idea of when they're leaky, and I think I got cut off when I was talking about this, all these ones, exponential, unit leaky, other ones, they're trying to have it both ways, right? We've got a very strong response on the positive end, so positive gradients are used and integrated very directly. And the negative ones are still used, but they're kind of softened, right? You don't want to focus on all the things you're going off in the wrong direction. But if you ignore them completely, you might have other problems. ReLU, I have a list of issues that you can get into with different ones. I don't remember right now, but ReLU has some challenges if you just use it pure on its own, because I think, yeah, if you basically have a model where you're initially not very close to things, it might have it's basically only responding to things that had strong gradients, right? But yeah, so there's a lot of these, and they're not really, I don't think there's any convergence on which one's the best. Different communities like using different ones, and just sometimes people get into a trend of one activation function being great and new. So it's just one of these things you can try out. But I think the default is still most times ReLU or exponential linear unit or something like that. It could be application specific. Somebody's asking, is it application specific or network specific? So it could be different parts of the network. So in the middle of the network, where there's hidden layers, usually something like this, where the negative response is very kind of constrained. But in a visual thing for images, you might focus on something very different. So it might be application of what type of image, but the fact that you're doing images versus voice or versus data. But in the final layer, which we haven't actually talked about, you might use something completely different, like sigmoid or softmax, because you want to get a specific output. But it's for these internal layers where you're learning that you have to think about. Well, not really think about it, because there's no theory to say which one's better. You just have to try them. I see what people find works. Okay. So each of those layers, then we get the same. We have the same function. We're kind of computing an output here. It's just more weights. But the idea here, then we're going to produce our actual label output together. And in the output layer, we're going to have another nonlinearity that helps us produce kind of an output answer. You could just look at the raw numbers directly from the network, but often you want to threshold it, or if you're doing classification, right, you want to say, well, pick the highest number, and maybe that's the one that we'll use. Or maybe you want a probability, and so you push it through a logistic function, and you get a probability output. There's lots of different ways to do that, but those are all the kind of components. So I'll just jump ahead here 2 slides because it fits this thing I have. So all the parts together, at least with the formulation I have here, you'd have basically the whole neural network can be written down, regardless how many layers you have, as some linear formula like this with series of weights for all the different layers, and some functions here that represent the nonlinearities at every one, and you're getting an output, right? And so these are your outputs for all your your nodes that you're going to have in the end, giving you your answer. So there's no mystery in terms of how they are built and work. The mystery is how to train them properly and make them do useful things. So, because there is this theory, which is why people got into using it originally, and people in the 90s were very excited about neural networks, was for a while that they should be able to fit anything, right? I think I mentioned this briefly before once, that there's this universal approximation theorem that any function that you could want that maps continuous inputs to finite outputs, you can do it, and you can do it to any level of accuracy, right? Which is pretty broad statement. So there should be some way to fit this. And this doesn't say with many hidden layers. This is with one hidden layer. And that's illegible, right? So this was just really this basic neural network with three things. The problem is you don't, how to set that up and how big the network would have to be is a problem. So you need an exponential number of hidden units in order to be able to learn it, right? And that could be in the number of data points, I think. So it makes that the network has to be very large. There's a very large number of weights to fit, and they don't have any guarantees about how long it would take to find it or anything like that. So theoretically, it's nice because it's a fully general function.